Welcome to Daily Curiosity.
The program where we discuss an interesting topic and teach some useful English along the way.
Daily Curiosity.
For curious people.
Hello, and welcome back to Daily Curiosity. I'm Carl.
And I'm Jane.
Jane, today we're diving into one of the most mystifying and terrifying concepts in all of physics, the black hole. We all know the basics. They have gravity so strong not even light can escape. But what's inside? What happens once you cross that point of no return?
That's the question that has haunted scientists for decades, Carl. It's always a pleasure to talk about the universe's most extreme puzzles. Let's start with the boundary. Carl, what exactly is the point of no return you just mentioned?
That's the event horizon. It's not a physical surface like the shell of a planet. Think of it more as a mathematical boundary in space. Once anything, let's say a star, a spaceship, or a particle of light, crosses that line, it can never send any information back out to the universe. The escape velocity exceeds the speed of light. It's the ultimate one-way door. You can enter, but you can never leave, or even scream for help.
So let's imagine a brave or a foolish astronaut decides to cross that horizon. What will happen to them?
Believe it or not, at the moment of crossing a large black hole, they might not feel anything dramatic at all. No flashing lights, no sudden tearing. The real danger comes from something called tidal forces, the difference in gravity pulling on your head and your feet. In a supermassive black hole, like the one at the center of our galaxy, those forces stay surprisingly gentle at first. You could cross the event horizon before anything terrible happens. But once you do, there's no turning back. You're falling inward and nothing can stop it.
I see. And from our side of the universe, it will probably look completely different. And weird, won't it?
Well, we would see the astronauts slow down as they approach the black hole. They would also redden due to gravitational redshift and appear to freeze at the event horizon, fading away over time. But that's just how space-time tricks our eyes. For the astronaut, nothing freezes. Time flows normally and they just keep falling, deeper and deeper into the unknown.
Okay, so they've crossed, they're falling. What's down there? Is it just an empty, dark pit?
That's where the known physics starts to stretch and scream. According to Einstein's general relativity, as you fall, space-time becomes more and more twisted. All paths lead inward. Eventually, you reach the center, what we call the singularity. It's a point of infinite density where gravity becomes unimaginably strong, and our usual laws of physics completely break down. At that point, everything we know about space and time stops making sense.
Infinite density? A point where physics breaks down? That sounds more like a mathematical error than a real place.
And that's the core of the problem, Jane. General relativity predicts it, but it clashes violently with our other great theory, quantum mechanics. Relativity deals with the very large, gravity and space-time, while quantum mechanics deals with the very small, particles and forces. They don't play nice together, and the singularity is where their fight comes to a head. Whenever physics predicts infinity, it usually means we're missing something, a piece of the puzzle we haven't figured out yet.
You're right, Carl. The singularity is likely not the final answer. We need a theory of quantum gravity to tell us what's truly there. In some theories, like loop quantum gravity, there might be a kind of quantum bounce, a bridge to another region of spacetime, though that's highly speculative. Carl, you mentioned the information paradox. How does that play into what's inside?
Ah, the million-dollar question. In quantum mechanics, information is never truly lost. If I burn a book, the ashes and smoke still contain the information of the words, at least in principle. But what if I throw a book into a black hole and the black hole eventually evaporates via Hawking radiation, as Stephen Hawking proposed? Where does that information go? Does it just disappear, breaking the laws of quantum mechanics? Or is it somehow stored on the event horizon?
And here's where it gets really wild, Carl. Some physicists talk about the holographic principle. It suggests that all the information about everything that falls into a black hole could actually be stored on its 2D surface, the event horizon, like a cosmic hologram. That means the inside might not be what we imagine at all.
Instead of just empty space and a singularity, the black hole could be like a 3D projection, a shadow of the information written on its surface. It's like the universe is playing a trick on us.
Exactly, and this idea could solve one of the biggest mysteries in physics. If the information is stored on the event horizon, it's never truly lost, even if the black hole disappears.
But that also raises another question, Carl. If the inside is just a projection, what does it mean for anything that falls in? Are we talking about a real physical experience or just an illusion of sorts?
That's the tricky part. From the astronaut's perspective, falling in would feel completely real. They'd experience stretching, tidal forces, and the unstoppable pull inward. But from the outside, the entire story of the fall could be written on the surface, as if the black hole is replaying it like a film, backwards and for everyone else to see. It's two perspectives that don't match, and that's what makes black holes so crazy.
So the universe might let you fall in and actually feel it, but at the same time, all the details of your fall are somehow recorded on the edge. It's almost like reality has two layers, one for you and one for everyone else watching.
Exactly, and understanding how these layers fit together is at the heart of modern physics. It's where Einstein's relativity meets quantum mechanics, and where our current theories are still struggling to explain the truth.
And let's not forget the classic science fiction favorite, the Einstein-Rosen bridge, or wormhole. Some solutions to the equations suggest the singularity might connect to another part of the universe, or even a different universe entirely.
But these are mostly mathematical curiosities. In reality, any forces involved would collapse such a bridge instantly. So I'm really sorry, dear interstellar travelers, no wormhole shortcuts today.
So, to summarize this conversation, we don't really know what's inside a black hole, at least in a concrete sense.
Of course we don't, and anyone who says they do with certainty is probably selling science fiction novels.
And that's the beautiful, frustrating thing. A black hole is the universe's ultimate secret keeper. It hides its core from us, forcing us to push our understanding of reality to the absolute limit. Studying them, their edges, their gravity, their effects on light and matter, is how we gather the clues to solve this mystery.
Exactly.
Carl, let's break down the key vocabulary from today's episode.
I'd say key physics terms. First, we have point of no return. That's actually a common phrase people use to describe a moment when you can't turn back. In the case of black holes, it refers to the event horizon, the invisible boundary around a black hole. Once anything crosses, not even light can escape.
Next is singularity, the center of a black hole, a point where gravity becomes unimaginably strong and our usual laws of physics completely break down.
Then there's general relativity, Einstein's theory that explains how gravity works and how massive objects warp spacetime.
On the flip side, we have quantum mechanics, the physics of the very small, which explains particles, forces, and the strange rules that govern them.
The information paradox is the puzzle about what happens to information that falls into a black hole. Quantum mechanics says information can't be lost, but black holes seem to destroy it. So how do we resolve that conflict? We still don't know for sure.
Finally, the holographic principle is a mind-bending idea suggesting that all the information about a black hole and everything inside it could be stored on its 2D surface, like a cosmic hologram.
That's it for today's episode. Thanks for joining us on Daily Curiosity.
Keep wondering and remember that the universe is so mysterious that even our most advanced physics and mathematics can't fully explain them.
We'll see you next time. Bye for now.
Goodbye.
Welcome to Daily Curiosity,
the program where we discuss an interesting topic and teach some useful English along the way.
Daily Curiosity.
For curious people.